Today we are going to see about the abrasive processes. We completed some of the machining processes as well as the machining fluids. So we are in the area of one of the multi-point cutting tool processes. You can say it is millions of cutting edges will be there in this process. So the surface roughness or the surface that you are going to get is completely random in nature, because the orientation of the abrasive particle as well as the shape and size of the abrasive particles will vary for process to process. So let me enter into the process. Till now we have seen the practical machining processes such as milling, drilling, other processes. At the same time, this is also one of the practical machining process. As for the present scenario is concerned, the grinding or the conventional type of grinding is considered to be one of the machining process only. But if you see as such, it is one of the finishing processes in the olden age, or nowadays also some of the industries they follow it as the finishing process. How you are looking at that perspective decides whether it is a machining process or a finishing process. If you are looking for this process like material removal process, you can say that it is a machining process. If you are looking like if this process as a surface finish process or the final finishing process, so it is as a finishing process. How you are looking, that perspective decides whether the today's lecture you are going to take or you are going to grasp as a machining process or the finishing process. We will see now about the introduction to abrasive processes. Whereas abrasive processes we deal in which mostly the common physics or the common example of the abrasive finishing process is the grinding process. Okay, that's why we talk in deep of the varieties or the advantages, types and all those things of the grinding process. And when we go on to the honing process, lapping process, super finishing, drag finishing, vibratory finishing and all other processes which are also considered to be one of the conventional finishing processes, we will see a little bit of these processes. Okay. In particular about this particular class, we deal with the grinding process only. If time permits, we will also see advanced finishing process if time is there, because number of hours also has a constraint. So if time permits, we will also see the glimpse just how and what are these processes and all those things. So in the grinding process, today we are going to deal with introduction to the grinding and grinding wheel specification and what are the problems and the solutions to the problems, what is robotic belt grinding process. At the same time, we will see what are the advantages as well as applications of grinding processes. So the grinding process is one of the ancient process where people used to make it to grind the materials to make medicine, so on. If you go to the villages also, mothers normally they do the chutney and all those things using rock as well as one of the woods. So they also grind that because so that you can swallow it easily rather than swallowing complete leaf. Just they do it, the chutneys, the red chilies and all those things, they will just, that is the conventional way of the grinding into the powder particles or grinding into the semi-solid where the particle size is very less. That is also called as a grinding process. One of the example is ball milling is one of the grinding process where you can crush the bigger particles into smaller particles. Okay. So not only the particles reducing, we also uses this process for finishing application or the machining applications. If you see this particular process where the shown is surface grinding, what is surface grinding and other things you will come across. Okay, so the surface grinding, just there is a workpiece, this is the workpiece and this is a wheel. The wheel is rotating at a certain speed like 2350 per RPM it is rotating. It is taken from the laboratory or laboratory only. So various variables that you can give, and you can generate or you can get the output responses. So the variables that normally you can give is depth of cut, that is nothing but how much depth you are going to give so that on the workpiece. The second thing is number of grinding cycles, that is complete rotation is one cycle. So number of cycles you can give 1000 cycle, 2000 cycles and all those things you can. So another important parameter is wheel speed, how much speed you can rotate. If you want higher speed, you can give the wheel speed higher speed. If you want lower speed, all those things. These are the some of the common variables apart from the wheel designations. Like you can also vary the abrasive particle size and abrasive particle type and all those things also you can vary. At the same time you can use the flood cooling. Since you have the knowledge of flood cooling, MQL and all those things, you can also vary there the volume flow rate as well as the pressure and all those things also can be variable. Okay, those are apart from the basic machining process of grinding. Okay, so if you see the three mechanisms of material removal, one is cutting or shearing of the material, that is dominating here. The cutting of the material is nothing but if you have sufficient depth of cut, what will happen? The abrasive particles will shear the surface and takes the chip. That is nothing but the cutting or shearing operation. Normally this is the dominant mechanism of material removal in the grinding process. There is a ploughing action also. Ploughing means if you see the farmers, whenever they do with the hull, what will happen? The material will come and it will fall in the previous one. So there is material will be not completely removed. That's a material will go into the previously existing surface. This is called the ploughing. Another one is rubbing. If you don't give sufficient amount of depth of cut and all those things, what will happen? The rubbing will take place. You might have seen the mechanism of ball burnishing and all those things. That is what is happening, and the chips will again smear on the surfaces and it will destroy the surfaces. So you also, if some people are working in the area of grinding or abrasive grinding processes or the abrasive processes, you come across the critical surface roughness and all those things. Since the roughness which I have told in the previous lectures has some relevance here. Turning, boring, these are the processes where you may not get good surface finish. If at all you want to get good surface finish, normally you can go for this particular process. But the critical surface roughness is a surface roughness beyond which, even though you change the input parameter, you may not improve the surface finish. Assume that if I am going to increase the wheel speed beyond, assume that I am not going to get the surface roughness, the delta change in the surface roughness is very negligible. That means that that is what my critical input parameter. So if my output parameter change is very negligible, then I don't want to move beyond that one. Why should I give more load to the machine? So that is nothing but the critical surface roughness. Okay. So grinding introduction, if you see the introduction, it is a finishing process. Normally it is used as a tool where you will have a numerous cutting edges, that is millions and millions of cutting edges, which are called as the abrasive particles, which are bound by the shape of the grinding wheel with the help of bonding material. Normally the bonding material will hold the abrasive particles intact. There are finishing processes, unbonded finishing processes. This comes under the bonded finishing processes. The wheel, if you see, the wheel is brought into the contact of the workpiece to be finished or the machined. The small edges of the abrasive particles cut very small amount of the material. So it shears the very small amount of the workpiece material, which is given as a depth of cut. The mechanism of the grinding process is same as conventional finishing process, that is the shearing, which means material removal by the process of plastic flow, and the deformation material leaves the permanent material from the in the form of a tiny chips are depend on your input conditions. It may also the microchips also. That is about the grinding. So the conventional machining versus the grinding process, if you see, the grinding is a self sharpening process. Self sharpening process means if the abrasives are gone, so new abrasives will come into picture. That is nothing but the grinding wheel is a brittle material basically. If a set of particles are, assume that I have a grinding wheel like this. So if the abrasive particles are here, if these abrasive particles are gone, what will happen? Next set of abrasive particles which are there will come into action, and it will do the machining operation or the finishing operation. That is nothing but the self sharpening process. But whereas if you see the single point cutting tool like turning process, your tool were gone means you have to change the tool. The geometry of cutting points, that is the abrasive grains, are sometimes maybe some textbook says that it is abrasive grains. Some papers or some of the textbooks they say that abrasive particles also is not well defined. That means that the shape and size normally you can get in a range. Assume that mesh size is 220, you can convert this into the abrasive particle size. I will tell you what is the mesh size, what is the abrasive size, what is the difference between whether they are linearly proportional or inversely proportional, all those things I will tell you. So these are all not defined, right? So some of the abrasive particle may look like this, some of the abrasive particles may look like this, some of the abrasive particles may look like this. So there is no particular shape, but if you are specifying certain mesh size, that means that approximately some are in the range of some of the plus or minus within the range. The size may be okay, but the shape may not be consistent in the abrasive particles. Abrasive grains are very small, therefore cut takes them also very small, and the size of chip ranges from this range. So that is very small for the normal applications. Therefore the conventional method studying the chip formation mechanics cannot be applicable here. Okay, so that is a difference. There the chip size is very high, the size effect will come into picture. The size effect is energy increases if the chip thickness goes down. So that is itself is a very big theory which I am not going to explain here. So in the conventional machining like turning process, here the chip mechanics is slightly different. The energy required per unit volume is very high. That means specific energy will be very high for the grinding process for the same material removal. Very high surface speeds, because normally the wheel speeds will be in the range of above 1000, normally 2000, 3000 will be here. But in lathe and other processes, normally if you see the conventional machining process, the RPM of workpiece you may not go more than 2000 or something. Here normally it also go approximately 5000 to 8000 or something also. So considerable side flow will be there because smearing action will be taking place. Now we are moving into the grinding wheel, which is a most important part of our grinding process is grinding wheel. There is a variety of grinding wheel, tool and cutter grinder, surface grinder, grinding wheel, tool and cutter grinding wheel. There are some other cylindrical grinding wheels, many more. If you see, depend on your requirement, there are a variety of grinding wheels are there. So wheel specification, the wheel specification in a common terminology goes like this, but it may be prefixed or superfixed by some other things like company name, they have their own codes. So that may be possible in some of the cases. However, we don't bother about certain company or something. So we bother about what is the basic specification of a grinding wheel. Okay. So if you see A36M7V, I am taking an example and I will explain you. Okay. So A stands for abrasive type, 36 stands for your grit size or particle size, and M stands for the grade, 7 stands for the structure, and V stands for the bond type. So if you see the abrasive type, there are varieties of abrasives. If there is a here, that means it is Al2O3, that is alumina type of abrasive particle. If C is there, it is silicon carbide. If D was there in the place of A, it was diamond. So that means I mean to say the type of abrasives which are going to use in that particular grinding wheel, which I am specifying as A36M7V. So next goes to the grit size, that is nothing but if the grit size is 10 to 24, coarse means very big or rough. Normally coarse size of grits are normally used whenever you are going to machine the material. That means that where your material removal is a criteria, not the surface roughness is a criteria. So if you go 30 to 60, it will be medium, 70 to 80 will be fine, and 220 to this one will be super fine. If your particle size goes 70 and above, normally you can go for the finishing process. These two you can go for finishing processes, these two normally you can go for machining processes. So grit size, coarse means very big. If it is big, the material removal will be also big. The surface roughness will be too high. That means that surface finish will be very bad. So if you see the M stands for the grade. I will tell what is the grade and all those things in the upcoming slides. So the grade specifies the bond strength. How firmly you are holding the abrasive particle, that is nothing but the grade. Okay. So there is A to H stands for soft grade, then J to P stands for medium grade, and Q to Z stands for hard grade. That means the soft grade means the abrasive particle is held very lightly. So it can be loosely delaminates from the bond. So if the hard means it is firmly hold, the abrasive particle is firmly held by the bond material. Next, the structure. The structure, there are two varieties of structures. One is open structure, another one is a dense structure. If it is 0 to 8, normally it is dense structure. 9 to 16, it is a open structure. Open structure means what? The particles distribution. Abrasive particles, how the abrasive particles are distributed on the grinding wheel. If it is too nearer to the consecutive particles, that means the dense. If it is there is a gap, then that means it is open structure. Next comes the bond. V stands for vitrified bond and type of bond. Normally the bond material is there, clay is there, metal is there, this type of things are there. So if the vitrified bond is there, that is one type of bond. If V here it is representing the V, that means that it is going to be vitrified bond. And if in case of V, it will be, if it is B, Resinoid bond, if it is S, Silicate bond, R is rubber bond, and E is Sherlock bond. Okay. So what are these bonds and all those things we will see in the upcoming slides. So mesh size, there is slightly confusion for the basic people who are looking at the presentation, that there will be a difference between mesh size and grit size or the particle size. Assume that I want to convert the mesh size. Mesh means, you know, our mothers normally whenever you have a wheat flour or some flour, they will use to sieve this one. Okay, that is nothing but the mesh. The square holes which are there on the net where the mothers used to sieve is nothing but the mesh. For a unit area, how many that square holes are there, that is decides the mesh number. If your mesh number is very high for a square, for the same area, that means that the particles passes through that mesh will be very small. That means your abrasive particle size is inversely proportional to your mesh size. Assume that if I want to calculate, normally there is a formula that is called 15.2 mm by mesh size, normally represented by hash, multiply by 1000 gives your abrasive particle size in terms of micrometers. Okay. So assume, for example, I have a 1000 mesh size. Okay. Let me take a 1000 mesh size. So it is there already, I am given here. So 15.2 multiply by 1000, why I am multiplying is to convert into microns, divided by 1000 mesh size. If it goes, what will happen? You will get 15.2 micrometers. That means my abrasive particle size, if I take the mesh size is 1000, so my abrasive particle size is 15.2 microns. In this way, one can calculate the abrasive particle size. Okay. So that is a relation. If I am increasing my denominator, that means that my particle size, if I go assume that 10,000 particle size, what will happen? It will be 1.52 micrometer. So that means that if I am going to increase mesh size, that the particle size is gradually decreasing. That is the relation between the mesh size as well as particle size. Again the same thing, just to show you the prefix and suffix, just I took this one match. Normally some of the companies, they will show the symbols indicating exact type of abrasive used, which is an optional basically. At the same time, at the end also, some of the manufacturers, they will give their private marking, which is also a optional. So that's why I dealt in this particular thing about this particular portion, which is a constant for all of the manufacturers, but this one and this one is optional for the manufacturers. So you don't worry, but this is what the commonly followed grinding wheel specification for any type of grinding wheels. So the selection of grinding wheel, if you see the shape and size of the grinding wheel is important. The kind of abrasive material, which is whether it is silicon carbide or Al2O3 or for the high material strength, the grain size, whether it is a coarse grain size or the particle size, one has to know. If at all I want to machine it or material removal, normally the grain size should be coarse and finer or better for the surface finish applications. So if you also see that the coarser wheels are normally used in the softer material and fine grains normally used in the hard and brittle materials. This is a common concept followed by the grinding process. Grade, hard grade normally uses for the soft wheel, soft materials machining, and the softer grades are used for the machining of the harder workpiece materials. Structure, open structure, bond material, these are all things will come. So among the wheel specification, normally A36, whatever we have seen, the grades as well as the structures, there are two things. If you see here, there is no much problem about anything here. If you see abrasive type, there is no confusion, because you are saying what are the abrasive type of abrasive particle. If you see the grit size, that means that you are talking about the particle size. If you see the grade, I will explain. If you see the structure, I will explain. Okay, that means that A and 36 don't have any confusion. Let me go directly into the grade, structure and bond. Okay. So I will explain you grade, structure and bond. So what is the grade? Define the degree of strength at which the bond holds the abrasive particles. So that means that how firmly the abrasive particle is held by the bond material, whether it is a vitrified bond or any bond. Hard grade means it is held very hardly, that means tightly. It bonds post very strong strength. If it is a soft grade, grains are released rapidly during the grinding process. So wheels grade symbols indicates alphabetically from A to Z, that is softer to the harder. That means If you see the grade, what is happening is, if I want to machine a softer material, assume that I want to machine a softer material, I should always go for a harder wheel, because the abrasive particles should be firmly hold so that the material removal takes place. Assume that if I am going to use softer wheel there, even though I am machining a softer material, my abrasive particles are dislodging, so which I don't want. For that purpose, obviously the person has to go for harder wheels. In case of harder materials, assume that I want to machine a very hard material. In that circumstances, I should go for softer grade wheels. So if I am unable to machine, what will happen? This will dislodge and the new cutting edge will come by the self sharpening effect of the grinding wheel, and it will try to remove the material. So if I am using a harder grade, what will happen? Neither it can remove the material nor it cannot dislodge the abrasive particle from the wheel. In that circumstances, what will happen? The abrasive particle will break and the surface will become glaze. Glaze is nothing but one of the problems of the grinding wheel. I will come across that one in the upcoming slides. That's why always keep in mind that you have to use the softer wheels for harder workpiece material, harder wheels for softer workpiece materials. Already I told you that this defines the particle locations. So space relationship of the grain and bond material, which is tells the grinding wheel. Density, dense structure means coarser grain spacing, close, it is close grain spacing, and open structure is relatively wider spacing. The selection of the grinding structure depends on type of work required, indicated the numbers in the range of 1 to 15. Normally, if I have the less value, that means the dense. If I have more value, it is the open structure. Now, there is an analogy that if at all I want to go for the machining of a harder material, machining of a softer material, which type of things that I want to. So type of material being ground, softer materials require greater chip clearance, therefore you need a open wheel. That means if I have a wheel like this, I have two abrasive particles here. If I am going for a softer material, that means that my material removal is very high. That means that my material will come and accumulate here. For that reason, you should always have an open structure, so that your grinding wheel will have two abrasive particles like this. The greater amount of material can be accommodated before it will become dull. That is why one has to go for the open structure. Finish required, normally dense wheel give the finish structure. Method of cooling, open structure wheels provide better supply of coolant. So if you see here, if I want to do the hard workpiece materials, there normally you should go for dense structures. Dense structure means so that the abrasive particles, number of abrasive particles will take part and it will, okay. You just there, the loading problem is not a problem. Wheel loading, the wheel loading is also one of the problems that I will discuss. Wheel loading is not a problem in the hard machine materials, so you can go for a dense structure. Okay, bond type, vitrified bond. Vitrified bond is nothing but, this is a clay. Normally how the bricks are manufactured and all those things, it is the clay or feldspar, the fuses with a high temperature. When the cool forms a glazy bonding between each grains that are there. Okay, so normally the brick is formed. Assume that you are having a grinding wheel shape thing. Just you embed the abrasive particles in the clay. You just go and do it the heating. So you will get a grinding wheel. That is nothing but the vitrified bond. Strong bond but break down readily because the surface is exposed to new grains. That is called self sharpening effect will be there. And bond suits for rapid removal of metal and not affected by the water or oil or acid. Okay, these type of bonds don't have much effect because it is heated with high temperature and it firmly bond a vitrified bond from the clay plus additives plus abrasive particles. If you see the second variety, that is called resin bond. Resin is a synthetic resins are used, generally operates at very high speeds that is 9500 speeds. Wheels are cool cutting and remove stock rapidly. If at all I want to go for the material removal processes, normally you can go for Resinoid Bond. The cutting off operations also, because wherever if you can make a very thin grinding wheels, you can make and you can use it for the cutting off operations of the workpieces. Okay, so like that. So now we will go for the rubber type of bonding, where the rubber bonding produces finishing. All normally these type of bonds are used for the finishing operations, because the rubbers are dominated by elastic characteristics, and they also possess the viscous nature. These are also used for thin cutting wheels because of its strength and flexibility, used for also for regulating wheels in centerless grinding process. Centerless grinding process we will come up in upcoming slides. There is a bond type. If you see the bond type, then shellac bond. Normally the shellac bonds are used for the camshaft, paper mill rollers and all those things, not suitable for rough and heavy grinding. These are very sophisticated grinding wheels for the simple small works like finishing or cutting off or something. Okay, these type of things will be used. And silicate bonds, these are all not used any extent in industry, because it is are the used principally for the large wheels, and for the small wheels there is necessary to keep heat generation to the minimum. Normally these are all used very big in size, so otherwise there will be a heat generation problem will come into picture. Silicate of soda silicate will be used, releases abrasive grains more rapidly. That means that the abrasive grains are released very fast. That means that it is held the abrasive particles loosely. Okay, the grade is softer grade. Another one is metal bond. Normally metal bonds are used in the electrical discharge grinding, electrical discharge diamond grinding. There are two processes or many other processes where you need the conductivity, that means electrical conductivity in the wheel also. There normally metal type of bondings were used. So what I mean to say is metal bonding are commonly used in electrical discharge grinding, electrical discharge diamond grinding, electrochemical grinding. These are many advanced grinding processes are there. There they will use this. So wheel problems, the everybody will have problems in the life. So fortunately or unfortunately, the grinding will also have its own problems. If you see the first problem, before seeing the problem, normally how the grinding wheel look like. If you see the grinding wheel look like and how it faces the problem, these are the grinding abrasive particles. These are the abrasive particles, and this is the bonding, and in between there is a porosity and all those things. This is a schematic diagram. This is a physical model or how you can represent that one, and you can also see the attritious wear and all those things here. So if you see practically how it look like, these are the voids. This is the bonding, this is the abrasive particle, this is the abrasive particle, in between you have a bonding. So these abrasive particles will get assistance from the bonding, and it will try to remove the material. If it is a softer wheel, the machined material will go and sit in these gaps. This is called normally structure, open structure of this one, the abrasive. This material will go and sit here. Okay, for that purpose it will be. Okay. These abrasive particles try to shear the workpiece material. That is how the abrasive wheel look like. Now the problems. The first problem is glazing. Glazing is nothing but, normally whenever if you see the hard workpiece material versus a hard wheel, with hard grade, normally you will get a glazing problem. Okay, what is the glazing? High strength material, hard metals, abrasive wheels get dull because of their edges get rounded off. That means if I have a hard wheel, that means that my abrasive particles are firmly bonded. If you are using against the hard workpiece, in that circumstances my abrasive particles are unable to remove the material and they break. Because these abrasive particles are ceramic particles, they will have a brittle fracture and it loses its cutting edges and become dull. Then the surface will become smooth and shining and creates, it will become less effective. That is, if you see in this particular picture, there the difference you can clearly see here. Wherever the workpiece is attacking or where they are contacting, there the surface is completely shining. Other area, if you see here, the other area is not shining. That means that this shining portion is glazed. You can say glazing. This also have good abrasive particles. This particular portion is good, this particular portion is good, but this particular portion is glazed. Okay, that is about the glazing. If you can also see the practically how it look like, because of the hard grade versus hard workpieces, the surface become smooth. I mean, not the workpiece surface becomes smooth, the surface of the grinding wheel becomes smooth. That is what you can clearly see in this wheel, as well as the same thing. If you can exaggerate, you can see here how the abrasive particles are become dull and inefficient. Okay, this is called the glazing. The second problem is wheel loading. If this is the process where the tiny chips are being accumulated in the gap between two successive grains, that is called gullet. Two abrasive particles are there, in between there is a gap, that is called gullet. If the abrasive particles are too near and if you are going for the machining of the softer materials, that means whenever you are machining a softer material with dense structure, then this problem will comes. If you see this one, what will happen, this white one is nothing but the material is occupied. That means nothing but material is loaded inside the grinding wheel. Whenever you have a softer workpiece and dense structure, then you don't have sufficient space between two abrasive particles to accommodate the chips. So I mean to say, there is no, I am not saying, there is a gap, very minimal gap. In that circumstances, very less time the wheel loading takes place, because the material removal of the softer workpiece is very high. That is what you can also see here, how the material is occupying between two abrasive particles. Okay, so this is about the wheel loading. Now, how to resolve these problems? These are the common problems of the grinding wheel, and the solutions, if you see here, one is dressing. So dressing defines the process of resharpening of the grinding wheel. This process used to fracture or tear away the glazed or loaded outer surface. That means that it is applicable for both the problems, that is glazing. If you see the glazing, that means that the sharp edges are gone and it becomes smooth on the wheel. So I have to remove that layer and I have to get a new layer. That is what the intention is. In the other case, if the abrasive particles are loaded, or it means that the gap between two abrasive particles or consecutive abrasive particles are loaded by the workpiece material, then also you have to remove, because in both cases, wheel loading as well as wheel glazing, the wheel become inefficient. So you have to find some suitable solution. That is, what you will do is, you just put a star dresser. There is one type of dresser, and you just run the grinding wheel process. If you do the, if just you have to run the grinding wheel, then the outer surface of the grinding wheel will remove by the star dresser. You can also use some of the diamond dressers where it will be like a point. This will particular grinding one will remove the outer layer and you will get a new surface which is having abrasive particles ready to go for the grinding process. These are the two varieties of dressers. One is a star dresser is there, another one is a diamond dresser will be there. Both will remove the glazed layer or the loaded surface and gives the fresh surface for the grinding operation. That is how you can come up. Next one is truing. Basically truing means because of the sudden jerks or something, what will happen, the grinding wheel loses its true geometry. That means that if I want a geometry, circular geometry, certain parts of circular T will goes off. Assume that I want a grinding wheel like this. Because of the sudden shock or something, if the grinding wheel become like this, what will happen? This particular portion became straight. I want to do the truing operation. That means that I want to make into a true geometrically circle shape. So for that purpose, I will use here also diamond indenter, and I will, since I am giving you constant depth of cut, this particular portion which are already worn out, those portions won't come in contact, but the other regions will come in contact and you will get a original circular surface. That is about the truing. Truing means you are going to get a true geometry of the grinding wheel. Okay, if you can see here how the truing is done, the dresser, this also you can use it for the purpose of the dressing also. Okay, because these are all can be used as a dressing, as well as you can use also for the truing purpose also. So if you can see the surface, how the surface is activated, our surface is getting back to the original true circular shape. This is going to help in getting the right geometry, so that there won't be much shocks on the workpiece and all those things. Okay, in this way it will help. The type of grinding process, since we are talking about introduction of particularly to the machining and machining fluids, I am not talking about any mechanics or something, because I already told many times that that particular course is floated or may be floated in the next semester, so people can take up that one. That's why I am not talking about any mechanics like any mathematical equations or something. Okay, so types of grinding, if you see horizontal grinding, vertical grinding, in as you see in the milling process also, you will have the horizontal grinding and vertical grinding, where your arbor axis where you will mount, if it is parallel to your workpiece, that is called horizontal. If it is perpendicular, then it is called vertical. So the first one is flat grinding process or the surface grinding process. If you see this, the surface is there and the wheel is there. Just the flat surface grinding wheel, if you see here, it will rotate about its own axis while the workpiece is fed beneath it. Normally that means that it is fed beneath the grinding wheel and it will do only on the surface. You can clearly see here how the surface, because of the high speed, the surface is getting machined and we will get a very perfect flat surfaces. For the perfect flat surfaces, normally you can go for surface grinding operations. Okay. Cylindrical grinding is another one, where you can see here, if at all I want the good geometry, you can get even by turning operation also, but the problem with the turning process is your surface roughness, that is F square by 8R equal to your RA will be, that means that will be a function of your feed as well as nose radius. Here there is nothing, because your abrasive particle is too tiny and it will remove the material. But only one point you should clearly notice in the grinding process is the abrasive particles all will possess the negative rake angles. No abrasive particles will be like a concave surface like that. All the abrasive particles, mostly it will be like abrasive convex particles. That means that you will have the negative rake angles. But the size of abrasive particles is too small compared to your nose radius. The surface roughness which you are going to get is very fine. As the particle size goes down, you will get very good surface finish. If you see, there is another cylindrical process that is called internal cylindrical process. If you are working on outside surface, it is external cylindrical grinding process. If you are working inside, that is called inner cylindrical grinding process. So, external and internal, just if you see, that is a schematic diagram. These are the practical diagrams. That is the schematic diagrams, and this is the practically visible diagrams that we have taken. So, if you see cylindrical grinding process, there are 4 motions which are involved in the cylindrical grinding process. Rapid motion of the grinding wheel will be one. This is the grinding wheel. Okay, normally the RPM will be about 2000. The slow rotation of the workpiece against the grinding wheel. So, the workpiece also will be rotated against the grinding wheel, so that machining will takes place and finishing will takes place. Horizontal travel of the workbench, and which is back and forth of the grinding wheel, and another one is in-feed wheel control. This is nothing but depth of cut. That means that you will give depth of cut like this. This will also move in this direction. So, that is, these are the 4 motions for the, this is external and this is internal grinding. Okay. You can see the grinding wheel here. The grinding wheel is fed in this direction. The grinding wheel is rotated inside the workpiece. So, this is how practically the internal cylindrical grinding and external cylindrical grinding look like. The profile grinding, if you see the profile grinding, normally these are used to grind intricate profiles. That means that if I want to machine or if I want to finish a profile, assume that I want to machine this particular profile, what I want is I need to generate a profile which is converse to that surface. Okay. So, if you can generate a wheel which is converse to my surface, normally if it comes in contact with a uniform surface of that cylindrical rod, what will happen? It will generate your specified form. These wheels rotate at very high speed while the workpiece is given rotation in the opposite direction to get, because since we have seen the cylindrical grinding operation, this also work in the similar lines, but only thing is that there the surface of the grinding wheel is same. Here the surface of the grinding wheel will be converse of what you want the product. That is what the profile grinding. If you see some of the examples, you can go by like this also, and this also. Like this, you can, this is one of the profiles. If you have a grinding wheel, you have to take into converse shape and just you have to give, so that you will get a proper profiles. Centerless grinding is another variety of grinding process where there are 2 varieties. One is given here. This is a external and internal, both surfaces you can do by this centerless grinding process. That means that there is no center. If at all I want to do the machining process in turning process, you have to hold the workpiece between the centers. That is nothing but normally the centered process. If there is no centers, then that means if at all I want to finish or the machine the irregular surfaces, normally you go for the centerless grinding wheel process. If you see, this is the grinding wheel and this is the regulating wheel, and the workpiece will be there and work rest will be there. So, it will, workpiece will be kept on a work rest, and grinding wheel will be removing the material, and the regulating wheel will be assisting the process. So, 2 things are there. One is centered grinding as well as centerless grinding. If you see here in the centered grinding, there it is the workpiece held between the centers. So, perfectly only I can do it for the normal regular shapes. If at all I have a irregular surface, then I have to go for centerless grinding process that I have told in the previous slide also. There is called, another one is internal centerless grinding also is available, where if you see internal centerless grinding, there are 2 wheels. One is bigger wheel, another which is actually the grinding wheel, while the smaller wheel one is used to as a regulating wheel. So, this is the regulating wheel actually, the okay, and the pressure rolls are there, supporting rolls are there, and all those things. In the regulating wheel is made up of rubber bond abrasives and has good frictional characteristics so that it will be intact. Okay. Normally, if you see here, the angles are not given. Anyhow, this is about the simple centerless grinding wheel process where you can do the internally if there is a irregular surface also. So normally tilted angles also there, some of the things are there in the mechanics which for the basic introduction you may not require. So what I mean to say is that if at all I have a irregular shapes like cams for example, I want to grind, normally you will go for external centerless grinding process. If you have similarly hollow things, you can go for internal centerless grinding process. There is another variety which is called a creep feed grinding where the depth of cut is so high normally. So if the full depth of cut stock is removed in one or two passes, normally it is called as a creep feed grinding, and very high forces are generated and very high rigidity and power is required in the grinding wheel for this one. Advantages of this process is increases accuracy, efficiency as well as surface finish. Burr reduction will be there and reduced stresses and fatigue will be there. Most important advantage of this particular process is that you can remove the material in less time. That means that you are going to give the depth of cut in a huge amount. That is, if you are going to give normal grinding 10 microns, 20 microns and all those things, in creep feed grinding you will give more than 1 mm or something in a single go. That means that it is purely a material removal process. That means it is the process that if you want to get certain shape or size in less time, you can go for the creep feed grinding. Normally, if you see here, the depth of cut is 1.6 mm in a one go. In normal grinding wheels, it may not sustain. For this purpose, you need to have a specially high strength grinding wheels for this particular purpose. So we are going to another variety of grinding process which are conventionally advanced. Okay, these are the old techniques, but there is some of the advancements are there in this particular process. So that's why it is called, which are the conventionally, but it is used for the adventional. So here you are use the robotic arm to against the belt grinding process. If you see here, it is a hip implant basically machined against the belt grinding process. Okay, these are the belt. If you see, this is also belt and this is also a belt. Continuously flowing belt is there which is moving, and so that the finishing of the implant will takes place. If you see here, can you see now the belt is continuously rotating and the robotic arm is putting some pressure on the metal. If at all I have a complicated surface to be finished, till now what we have seen, if I have an irregular shape up to some extent like convex, concave and all those things, internal surfaces, cylindrical surfaces as well as most importantly flat surfaces. If at all I have still more complex surfaces, then we can go for robotic arm assisting belt grinding processes. These are one of the advanced techniques, but using the conventional mechanisms like belt grinding and all those things. You can see here it is polished against the cloth belt. So there is called buffing, there is called polishing of this complex surfaces and all those things. There also they will, this particular portion is a robotic arm, this is a robotic, this is the arm which can give the motion as per the requirement. This is one variety. If you see, there is second variety. There is also grinding wheels which where you can put the complex surfaces using the robotic arm. Here also not only the belts, you can also use the grinding wheels itself. That is what I want to show. If you see here, the second picture, this is figure 1 where hip implant stem is fabricating or finishing is going on. In another case, hip implant head is going to finish here. If you can see here, the finishing action is taking place on the head. Okay, That's how the normally bioimplants are. For example, I am taking in this one as a bioimplant is a hip joint, because you need a good surface finish on the head. If it is not there, normally the motion of particular person will be very less. Okay, so you need very good surface finish on that one. If you see the knee implant also can be machined in two ways, or the finished in two ways, that is called the belt grinding. If you see here the belt grinding operation and the knee implant in the figure 1, how the knee implant getting different complex motions from the robotic arm, and it is fed against the belt, okay, and it is getting super finished, or it is getting finished. In another case, if you see the knee implant is fed against the grinding wheel itself. So in this way the complex surface is finished. So grinding process has ability to do simple to complex shapes, and it also can give very good surface finish. Depend always, please note that the surface finish, if you want, then you have to give very low input conditions, so that the interacting forces between wheel as well as the workpiece will be less. Okay. These are the advantages and applications. If you see the advantages: dimensional accuracy, good surface finish, form, locational accuracy. Normally this is applicable for hardened or unhardened workpiece materials. Applications, huge amount of applications are there, like surface finishing, slitting, parting, descaling, stock removal, finishing of the flat, and cutting, as well as what we have seen the last is it can also useful for the finishing of the complex surfaces. The summary of this particular class, if you see, the summary goes like this: introduction to the grinding we have seen, followed by the grinding wheel specification, wheel problems, as well as the solutions, and at last we have seen the one of the applications of the basic physics in terms of the robotic arm, belt grinding, and all those things, followed by the advantages and applications. So this is one of the conventional fascinating process where you can take up, if you are a master's and PhD student, you have a lot of scope, okay, to do the research. It is a evergreen process, and if you can find lot of papers, still you can do lot more research in it. And, okay. Thank you for this lecture as well as for your kind patience. Hope you enjoyed the course from the basic of the grinding to the advanced version, one of the versions that I have shown as a glimpse. I hope you enjoyed the class. Thank you.